Okay, now we're in Edmond Storms Cold Fusion Lab. It's a little private experiment going on. You want to explain it to me?
Yeah, well, this apparatus is designed to sputter various materials onto a target and then test the target for LENR, for the low energy nuclear reaction, looking for radiation. They're not looking for heat.
Okay.
Looking for, because all nuclear reactions have to get rid of their energy somehow or another. And they normally get rid of it by giving off energy in some form. Theory has it that, and also a certain amount of observation, that the energy is given off as photons. In other words, high energy light. So there's a Geiger counter inside and there's a Geiger counter on the outside looking for any radiation that might be given off. So if I see radiation, then I say, okay, I've made a nuclear reaction. So on this side I test for the activity, and on that side I make the sample. And right now the sample is being sputtered using this power supply, gradually building up a material on a target that I'm hoping will be active. And the target looks like this.
You guys are getting your glasses out.
He's putting his away, I'm pulling mine
It's a
out.
piece of copper, and the sputtering has taken place in that little region there in the center, which then, if it becomes nuclear active, will give off enough radiation for me to see it with the Geiger counters.
Now you're sputtering to create a radioactive material?
I'm sputtering to create a material that has the ability to initiate the cold fusion reaction. I mean, most materials will do absolutely nothing. And even materials that you make on purpose, only a small fraction of it will do anything.
Okay.
But you have to have that small fraction to see anything, but most material won't produce the effect at all. So I'm trying to make a material that has enough of that small fraction in it that when, the nuclear reaction occurs, I can see it looking at the radiation. And you do need to watch your head.
Nice.
That's
there.
why I got a brim on my hat.
Yeah, right.
So you're making the material over here.
Yeah.
And how are you making the material? Is that a magnetic resonance?
No. Look down inside there. You can see a discharge. You can see a plasma discharge inside.
Oh, yes. Okay.
That plasma discharge is causing atoms of palladium that's on the emitter to boil off and condense on the target.
Oh, I need one of these.
Here, thank you, got one.
I need one.
Thank you, got one in that truck.
I think I got a couple of them.
Yep.
Something similar.
So you got a palladium rod in there.
Yeah.
And you're emitting them off to the plate, which is grounded. So you're like a electrolysis effect.
Well, it's in gas. It's the plasma. The plasma bombards the palladium with ions. That causes palladium atoms to come off and scatter in all directions, and some of them condense out on the target and builds up a layer.
And you're using copper for the target.
Yeah.
So in a reaction of cold fusion, or in an excess energy reaction, simply put, if you had 10 watts in, and if you get 14 watts out, that's something to study.
That's enough to tell you that it happened. It's not enough to make it practical.
Right.
Now, the way you make it practical is to create enough of the active material in there that you're getting 100 watts out when you put 10 watts in. But you can't do that. That's very, very rare. There have been people that have gotten up to that neighborhood, but very, very seldom.
If you, this is just, I can look this up or you tell me. If you've got a piece of metal that gets 150 degrees is there any indication how many watts that 150 degrees is?
Yeah, it's called the heat capacity, and you take the heat capacity and multiply it by the temperature, and that gives you the amount of energy being contained in that material.
Okay. So if you've got a piece of 5/16 rod and it's 180 degrees, there should be a calculation telling me how many watts that is.
Well, see, watts is power. It's
Okay.
not energy.
Energy.
It's watts times time is energy. So it will, power is how fast the energy is coming out or going into something, not the total amount. So when you ask how much energy, let's say, a rod can hold, you have to say, okay, a certain number of watt seconds or calories. A calorie and a watt second are essentially the same thing.
Okay.
And so, but when you're talking about watts, you're talking about how fast it's going in or out. Now, if you want to know how much energy is in a material, you take the temperature and you multiply it by the heat capacity. You look up the heat capacity in a table. And most materials, the heat capacity is measured, and you can just look them up in a table. Just multiply it by the temperature, and you got the amount of energy that is contained in that material.
Thank you for that, because that's it's a huge question of mine, because I see when I drop my electrodes in my solution, there's two things that happen in the solution for me that are different than what I would normally expect. The first thing is regular salt water, the pH goes way up over 14. I mean, it pegs the meter at 14, okay, in very short time. The second thing that happens is I'm growing the algae in there. I can arc the top of the water, and I kind of showed that on my videos, and that rod is cherry red hot.
Sure.
But I'm not using that much energy to make that rod hot.
Well, you are. See, in order to make something cherry red, well, cherry red is like 800 degrees. And so to get a piece of steel up to 800 degrees, the heat capacity of steel is about, what is it? It's in the water. It's about 0.7 calories per degree times 800. So let's say 500 calories you're putting in to get to that temperature. Well, that's not very much energy. That's a fairly trivial amount of energy. Now, it's giving off energy at the same rate that you're putting it in. Otherwise, it would keep getting hotter.
Right.
And now you can calculate how many watts it has to be giving off based upon how many watts you're putting in. Well, if it's electrolysis, you're putting in a current and a voltage.
Right.
Multiply the two. That's how many watts are going into it and how many watts are coming out of it as a result of its temperature. But there's very little stored energy there. Just because it's hot doesn't mean that there's much energy. It depends on the magnitude. I mean, for example, an electric light bulb has very little stored energy, yet it's really, really hot.
Correct. So, I guess the question is, in the cold fusion, how are they storing the energy?
Well, you're not storing it. You're releasing it. That's the measure. You're measuring the rate of release. Let me show you what a calorimeter looks like.
Okay.